All right, thank you everyone. For those just joining on YouTube, this is the Denver, Erlang, and Elixir meetup. Today's date is Monday, November 6, 2023. The meetup tonight is sponsored by Praxio.io, which is a security platform for Elixir and Phoenix. Also available through the company are consulting services related to Elixir security and developer security training focused on Elixir. The main event for tonight, big thank you to Tyler for speaking tonight. Fantastic hacks and where to find them. Tyler also spoke at ElixirConf this year, and we're just very grateful to have him talking tonight. Okay, I can see it.
Okay, all right. Everybody hear me? All right.
Yep, you're good. You're good.
Okay. Hi, everybody. My name's Tyler. I'm from Kansas City, Missouri. This talk is something I put together a couple of years ago, inspired by this talk by Miriam Pena at ElixirConf 2019 Beam Extreme. If you'd like to follow along on your own device, if you go to tylerayoung.com, my blog, it's like the first post there. What did I? Yeah, if it's not there now, it'll be there soon. Yeah, so I've been in the Elixir world since 2019. I worked on a flight simulator called X-Plane, and we built this massive multiplayer game server in Elixir, and it was kind of like I shifted the whole direction of my career after kind of getting addicted to Elixir, as I know many of you have. Until recently, I've worked at Felt on a collaborative mapping software. We use Phoenix channels, communicating with a React front end, and build what has been called the Figma of maps. And then recently I started this project called Sleep Easy Website Monitor. That's at sleepeasy.app if you want to see. And using Elixir to monitor websites for both uptime and things like broken links, SSL certificates expiring, domain registration, all that stuff. Yeah, so this talk is about CPU performance. And if you've been around Elixir, you'll know that CPU performance is not often the thing that constrains us. Anytime you talk about performance, you have to quote Joe, make it work, then make it beautiful, then if you really, really have to, make it fast. Because it turns out performance is usually good enough by default. And so the first rule of performance is if you think you have a performance problem, you should profile first. You don't want to be rewriting chunks of your code base without profiling, because you might end up making things worse. You might end up introducing a bunch of changes without needing to. And certainly, this talk is called Fantastic Hacks. There is some hacky stuff that you probably shouldn't do at all, but if you do need to do it, make sure you have a really good reason. So the picture here, the image is eFlame, a nice flame graph library. So you basically wrap a function call, and it'll show you where that function spent its time during the execution. There's also Flame On, which is a library from Mike Benz that does the same thing, but it's hooked into Phoenix Live Dashboard. So if you have a Phoenix app, this is a really nice way to get those performance profiles. You can dig in and see where the time's going. So if you do profile, what you'll probably see is that database queries are the thing that are holding you back. In most web apps, if some page is slow to load, it's almost certainly because you either have a bajillion queries. Maybe you've got an N+1 query where, in this example, you're loading a bunch of events individually when you should be loading them all at once, from the list of IDs. Maybe you've got an N+1 query, maybe you've got, complicated joins, whatever it is. Indexing can help on that sort of thing. You should look at your joins. Obviously, the downside of just add more indexes is that it uses more disk space, and eventually you run into issues with insert speed. I'm not the database guy, so we're going to breeze right past this and assume that you're in a situation where you actually have a CPU performance problem, not a database problem. Okay, so a little background. Elixir solves a whole bunch of concurrency issues. Like it makes this whole class of issues impossible because we are message passing by default. Without any shared writable memory, you can't shoot yourself in the foot in the way that you can in many other languages. And on top of that, garbage collection is easy, right? Because we can do garbage collection per process. We know, this process is done using this bit of memory. We can go ahead and free it up and that sort of thing. The downside of message passing is that it's basically just memcopy, right? If you need to send some data between two processes, it's a copy. And all of those copies can add up. A few exceptions to the message passing by default rule: atoms, binaries that are large, literals, and then code. And this is kind of foreshadowing of an optimization we'll talk about later. So if it turns out that memory copies are the thing that's slowing you down, why not just do less of that? The silly place to start is like, look at whether something needs to be split out into a process. Maybe you're doing it in a, you've got a gen server, or you've got, maybe you're sending it across channels. Can you bring the computation to the data itself rather than, serializing it between processes? And then you can also look at places where you're like rebuilding intermediate data structures over and over and thereby generating a bunch of copies. Like, I think, yeah, I do have the slide. This is an example from a PR where I found in our production app that doing these calculations, what this does isn't important, but I think it's calculating the size of a polygon. Anyway, we've got a bunch of segments. If you look the top deleted version, we've got there's one copy of the data with the zip, and then we're creating another copy of the list. Now the drop of the first element is basically free, but the drop of the last one is another copy of the entire list. And then we were doing a map, which is another copy of the entire list, and then a max by another copy. And turning that into a single enum.reduce was like more than a 2x performance increase, just by reducing the number of intermediate copies. Okay, so that concludes the section of the talk where it's like, this is generally applicable. Nobody's going to look, give you the side eye if you implement that. We're entering the danger zone. So let's say you can't do fewer copies. You can choose a better data type. So for instance, a data type with lower overhead. IOList is better than concatenating a bunch of strings together into a big binary. By default, Phoenix handles IO lists very nicely. For those of you not familiar, an IO list is it's a list of a bunch of tuples or smaller strings, which then get splatted all together to form a complete response. You can also choose ways to operate on the data that are lower overhead. BIFs are binary implemented functions. This is most of the things in the kernel module are implemented in terms of C function calls rather than Beam code, and thus you get the benefits of just lower overhead. And similarly, pattern matching is faster than function calls. And you can prefer data types that have better memory locality. Binaries are better than character lists. Tuples and by extension records are more compact in memory than lists and maps and structs. Your coworkers will not appreciate if you go and replace every instance of structs with records. But if you profile and there is a place for that, sometimes it works. One instance of this that I ran into was we had a database of all the airports in the world. It was an in-memory database, right? It's just a data structure that we were accessing frequently. Switching to tuples made the thing quite a bit more efficient to look up into, because we've got 36,000 things that we're accessing basically at random all the time. An aside, what is memory locality? This example, Let's suppose that the number line here is memory laid out, right? We've got all these bytes. In the top example, we've got A through H. They are in positions 0 through 7. They're contiguous in memory. And the way that CPUs work is they have to read pieces of memory in terms of in the cache line size. So your CPU can read, let's call it 128 kilobytes from memory at a time. And so you don't get any speed savings by using less than that. So if you had A through H as a list, under the hood, that's going to be stored as like 2 bytes for the A plus a pointer to the next thing. So you've got 4 bytes there, and then it's going to have to jump somewhere else in memory to get the B, jump somewhere else to get the C, and so on. And so this might turn into, let's call it 4 cache lines that you have to read. And they might not be linear like this either, right? The C and D might be totally elsewhere in memory compared to the A and B. The closer things are in memory, the more the CPU can blast through your computation, right? So why does memory locality matter? Okay, we know what it is, things that are close in memory. So this is a graph of the 20-year period from 1980 to 2000. This is what RAM speeds did. They got 8 times faster. Not bad, right? Except when you overlay the CPU speed increase in that same period, RAM is still graphed here, but it is 4 pixels tall on the screen. CPUs got way faster at a much higher rate than memory did. And this same trend has continued. If anything, things are just getting worse. Similarly, this is the number of clock cycles that it takes to get a piece of data from the L1 cache, which is like the smallest cache and the one that's closest to the CPU's registers, get that into registers to actually operate on. So L1 cache is very fast. It's less than 1 cycle to get that loaded. L2 cache, 7 cycles, so quite a bit slower. If we should put main memory on here, you're looking at 100 cycles to read something from memory into the CPU to operate on it. And God help you if you have to go to disk. Even a fast SSD, just there's no comparison. So the tighter you can pack things in memory, the faster you can work with them. And the weird thing is with modern CPUs, like if you can have your data contiguous in memory, you can blast through it at an astronomical speed. Like anybody who is optimizing, you're not at that point, right? You're not at the point of everything being contiguous in memory, because there's not going to be a performance problem realistically in that case. Okay, so that's why tuples are, of course, contiguous in memory, whereas lists and maps and structs, you're going to be doing pointer chasing and thus loading from different parts of memory that the CPU's prefetcher is not good at predicting. Okay, so the next technique for improving speed, can you move computation to compile time? Anytime you can just not do a computation at runtime, it's almost always a win. The only time that this might not be a win is if you slow things down because of code load. So like if you are loading, if you've got so much additional binary generated that, you know, in the course of running the program, the CPU is having to jump around too much in the binary to be efficient. The more common cost is at compile time. I talked about that 36,000 airport in-memory database. That thing was slow to compile. Granted, that was on like OTP 23. It was a while ago. It's actually gotten quite a bit faster, but yeah, there's a cost to that. So let's say you can't do compile time. Caching in ETS, this is a shared in-memory data structure that's available across the beam. This can share data between processes in a way that is pretty quick to access. It is wildly faster than sending that data to a gen server and then trying to pull it out from other processes. Concurrent reads are they're supported without a process bottleneck. And as long as your table is protected, which is the default, it's only writable by the process that creates it, and thus you're not going to get data races where two processes read and try to update it concurrently, and you get like an inconsistent state. The downside of this is that you do still have to copy the data both in and out. So if you've got a data structure that's many megabytes, the read time is still a big penalty. And as it says, there are exciting new possibilities for race conditions here. If you decide to go away from the one process writing model. If ETS is not an option, but you do still have some OTP goodness going on, you can skip gen servers and just use raw processes that you spawn the process, you have it receive messages and that sort of thing, by avoiding the layers of indirection that gen server gives you in the name of reliability. You can save something like 80% of the call time into that process, at the cost, of course, that the code is going to be harder to read and less idiomatic. Your coworkers will definitely give you the side eye for this one. All right, and that ends the danger zone, and now we're entering the part of the talk where it's like, this is probably not a good idea, but it's kind of fun to know that it exists. The process dictionary. This is like the gold standard in terms of hacks that you shouldn't touch but are awesome. So each process has this private data store. You can do process.put to associate some value with an atom key, and it is incredibly fast to access this. The speed advantage over ETS at large sizes is astronomical, because of course there is no copy either in or out. You just get, it's a pointer to the value in your process. Now the downsides: destroys referential transparency. The warnings around this in the Erlang docs are very funny. They are very serious. Destroys referential transparency means that if your process, if your function relies on this, it's no longer the case that given the same arguments to a function, you'll get the same value out, right? You've suddenly got this global state that you're reading from, which is kind of doing the spooky action at a distance thing. Makes debugging difficult, says the Erlang docs. And you get no garbage collection for the life of the process. So if you're putting a bunch of data in there and updating it constantly, you could eventually run your system out of memory. And it survives, changes to the process dictionary survive catch and throw. So if you are in the middle of, let's say you're updating some records in the database and you store it first in the process dictionary, and the write fails and you get an exception, your process dictionary change will stay, even though you unwound the rest of the stack with your try catch. So scary stuff. Persistent term is another one of those fun hacks. Persistent term is not linked to your process. It's another data store, optimized for heavy reads and infrequent writes. So this is useful if you are like producing some data at the start of your maybe when your app boots up, and then reading from it constantly, but not updating it very, very frequently. It gives you constant time access with neither locks nor copies, which is about the gold standard in terms of read speed. And it is way faster than ETS. However, if you end up writing too much data to it, you can trigger a global garbage collection pause. And the amazing thing coming to Elixir from other languages, from the JVM and that sort of thing, is that you pretty much don't have to think about the garbage collection. You don't have to tune the GC algorithm or any of that. You don't have the entire application locking up when the garbage collection is triggered. This gets you right back into that world. So use sparingly at most. Next, by default, Elixir's scheduler, the Beam's scheduler for different processes is it uses a fair scheduling algorithm. So basically each process gets some amount of computation time, and if you run over that time, the scheduler will say, okay, we're going to give another process a turn. And this is how you get those demos where one process is completing the computing the millionth digit of pi, and another is computing the eighth, and the eighth, finishes even though the millionth computation is still running and running and running. But you can override that behavior. You can use the process.flag function to kind of make your process jump in the scheduler's queue. You can say, this is more important, prioritize this. It makes the thing faster, but of course you can starve the scheduler, right? And you can make that process that was calculating the millionth digit of pi be the only thing that gets to run and deadlock your whole thing, your whole system. And okay, a couple more tips that are very in the weeds. Don't shuffle argument order. If you look at the decompiled binary, the assembly generated by a beam function, a function call, changing the argument order, it leads to like extra copies, like extra, shuffling things around. So you want to call, if you've got a deep call stack where you're passing like the same arguments, keep the argument order consistent. I like this rule because this is also like nice for the developers. It's nice for the humans. If you've got a module that's operating on the same types of stuff, keep the argument order consistent. Function overload function overload order matters in some cases. This is interesting to look at if you've got, let's say you've got 3 function heads, and the first 2 are like kind of catching edge cases. Maybe they're catching, the empty list case or something like that. It is better for you to have the most common path that your code's going to actually traverse, the most commonly used function head, put that at the top, because under the hood, those function heads are basically implemented as like if else, right? It's like 3 if else blocks. You want the thing that gets hit the most to be the very first one. And if all else fails, you can use this decompile library, produce the assembly that your binary is going to actually generate, and kind of stare at that and go like, okay, why is this doing more work than I think it should? And when all else fails, of course, there are Nifs. Nifs let you bridge a systems language into your Elixir code. Ziegler and Rustler are common ways that people package this stuff. It gives you access to better data structures. List kind of stinks. It is not good for memory locality. It's not great at random access, and you can get that by bridging into another language. This bridging does have a cost. Some people will tell you that you need large batches of work, so you don't want to bridge into the Nif for like, let's say every addition operation or whatever. You want to send like a batch of work to the Nif and do many additions at once. In some cases, I've seen benchmarks where that doesn't really matter. Like the Nif performance is good enough that it doesn't make a difference, or it's perfectly usable with single operations. Obviously, your mileage may vary. Give it a try. See what you need for your system. The danger, of course, with Nifs, aside from it being rather unergonomic and not idiomatic, is that if you crash a Nif, let's say your Nif is written in C or C++, you will bring down the entire app. That stinks because like one of the core benefits of the Beam is like you can't bring the thing down, right? It's so resilient. Okay, that was a whirlwind. Happy to discuss. Yeah, this is my summary slide. That's all I've got.
Nice, thank you. I'll stop the recording right now, and then I guess we can go to questions.